All right, and this brings us to the third and last presentation in this session, and it will be held by Aziz Niyazov from University of Toulouse, who will talk about dynamic decals.
Good morning, everybody. My name is Aziz, and I would like you to present Dynamic Decals, Pervasive Freeform interfaces using constrained deformable graphical elements. This work is done under the supervision of Nicolas, Mellado, Loic, Barthe, and Serrano. I would like first to start with the pervasive interfaces. What are they? The pervasive interfaces means that the interfaces can be everywhere on the environment. Here you may see the examples of such interfaces for the entertainment purposes that already exist in museums or shopping malls. Beyond the entertainment, there are more complicated interfaces. For example, to augment the workspace and to make work more productive. Projection-based interfaces are relevant in several contexts, such as smart buildings, university classrooms, as you may see here, to provide pervasive access to contextual data, online resources, and interactive content. However, such interfaces, such types of the systems leads to presentation and interaction challenges. The first challenge is the efficient space coverage. Imagine a student at the smart campus. The classroom is segmented by projecting interfaces on the table. As the class starts, the system projects the file navigation showing a grid of folders. Here the table is circular and the projected interface is squared. So a student cannot use all the available display space. On top of that, there is a handling of object occlusions or inner holes inside the display. Imagine the teacher starts providing session instructions and a student needs to take some notes. He opens his notebook covering by part of the interface. The student is no more able to interact with the content below the book. Then the student needs to carry out the brainstorming session using post-its application. The student starts linking and adding post-its. He also needs to manually displace all post-its to the available display space that is not covered by the physical object. Also, if he moves the book, he needs to rearrange all the post-its again. The previous works tried to overcome these challenges, but with some limitations. To handle the object occlusion, the approach was to reposition all the occluded content in another area of the interface. However, the main limitation, it's not space efficient because it does not maximize the space occupation. It's just rearranging rectangular windows in the available display space. In other previous works, the graphical user interface layout adapts to a non-rectangular display by content mapping or content deformation. However, in these works, the whole interface is warped, which impacts the visibility of the content, particularly the UI elements close to the edges of the window. Our approach is dynamic decals. By decomposing interface into small graphical elements, so-called decals, we build a system that can deform and move each decal independently from each other. In this presentation, first I will talk about our contributions, then about the study on shape deformation, decals constraints, and user evaluation, as well as the application and limitation in future work. To tackle the problem, we propose a novel solution based on two contributions: the design and implementation of graphical deformation of dynamic decals, and the design and implementation of constraint-based approach to optimize the layout of decals. First, I will present you decal deformation model to preserve content when two decals collide. In order to deform decals, we represented them as the field functions. We implemented square decals, square with rounded corners and circular. This is the example of content deformation of two decals that is represented as the field function of two decals. Here you can see that G is the deformation operator. Then you can see here the results of the deformations. We implemented 4 types of it. We made the inside part overlap or squashed, and also we either preserve boundaries or blend them. Then we did a study on the shape deformation. The survey consisted of two parts. The first part is the pairwise comparison. We decided to only compare collisions between decals having the same shape and the same content. The second part is the shape preference. The task was to rank the shapes in order of their preference for each type of the content, namely icons, images, and text, and motivate the choice. We asked 27 participants to make a pairwise comparison. We asked questions of which deformation is nicer, clearer, and more associated with the group. We did this for 3 shapes, 4 content types, and 4 deformations. Overall, we had 54 of pairs of animation. We made a statistical test for pairwise comparison. The results show that for icons and images, participants preferred square, rounded shapes, and for the text is simply square. For all types of the content and shapes, it is preferred to have overlapping union deformation. Our second contribution is the design and implementation of constraint-based approach to optimize the layout of decals. Imagine that you have a rectangular interface as on the left, and you want to see the content of it in a freeform shape as on the right. What is the way to handle the content? The solution we propose is the constraint-based layout optimization. Each constraint is defined as the cost function, and layout optimization is defined by minimizing some of the cost functions. We implemented 3 constraints. GAMUT. Okay, so the first one is the GAMUT constraint. In our case, the GAMUT is the overall display shape. The next one is the distance constraint. And also we implemented the alignment constraints. The GAMUT constraint is used to keep the decals inside the display area. When the decals is outside of the GAMUT, the system penalizes the decals and moves it inside this display area by minimizing the cost. Then we have the minimum distance constraint that is making the decals not overlapping with each other. If one decal gets to another decal, if one decal gets too close to another decal, the decals will be penalized. The closer the decals to each other, the higher the cost will be applied. For the maximum distance, the system is not allowing the decals to move too far away from each other, keeping them at the maximum allowed distance. As you may see here, the alignment constraint is pushing the decals towards the line. So the decals has one horizontal alignment point. We made an automatic quantitative evaluation of our constraints. To do so, we measured the percentage of a content preserved and the layout simplicity. And also we automatically computed these metrics. For this, we tested 4 interfaces with different conditions. Here are the different combinations of constraints applied using our approach, where the gray disk is the MAC. On the left, we only apply GAMUT, minimum distance, and minimum distance constraint, and we name it decals mean. In the middle, we apply GAMUT, minimum distance, and alignment constraint, and we name it decals align. On the right, we apply minimum distance, we apply GAMUT, minimum distance, and maximum distance constraint to keep decals with the same color as group. Thus, we have the name decals group. We implemented 2 baselines, no deformation and warping. No deformation display condition is when the interface is simply occluded with the physical objects. Another baseline is warping, where the whole interface is deformed due to the presence of physical objects. As the comparison, we show in this slide the decals mean and decals aligned with the same interface. On this slide, you may see the differences between warping and minimum distance constraint when applying the solver. On top, having a 5x5 grid of folders and applying warping, the content is either deformed or hidden completely. This impacts the content perception. When the interface consists of 2 display areas, the middle column is hidden completely. Same we may see with the donut-shaped display area. On the other hand, using decals mean, we have all the content visible inside the display area. Here is a difference between applying GAMUT and distance constraint in decals min and GAMUT distance constraint, minimum distance and alignment constraints in decals aligned. In the first row, the content is simply adapts to the display shape, whereas applying alignment constraints keeps the graphical elements in a specific structure. After making an analysis of data, the results show that dynamic decals improve content preservation and the alignment. Next part is the user study. The user study was conducted at 65 inches tabletop, and the evaluation consists of two parts. The first part is focused on the interface deformation by object occlusion. We ask participants to put the physical objects, which is a mug in our study, on two different positions to occlude the interface. Then we ask to make the evaluation in terms of overall interface being nice, its content visible, aligned, and grouped. The next part of the user study is focused on the interface, on the perception of the interface in the freeform shapes, including display area split by two and a donut, which is a disk with the hole in the middle. This time we ask participants to evaluate displaying conditions applied on these interfaces. Here is the example of 3x3 grid of folders, a grid of images, applying GAMUT constraint, minimum distance constraints. Compared to the baseline, we obtained the decals aligned and decals grouped display conditions were more preferable among participants in terms of all metrics: aesthetics, content visibility, content alignment, and content grouping. Also, we asked participants to answer a question about the system usability. We use standard 10 questions Likert scale to measure SUS. According to the results, displaying an interface applying grouping and alignment constraints were chosen as the best techniques. To sum up, our studies show that dynamic decals improve interface aesthetics and content visibility, while preserving content alignment and content grouping. Our approach can have many applications beyond our initial augmented classroom user scenario. Here you may see different scenarios where we apply dynamic decals. From left to right and top to bottom, you can see the casual image gallery on a freeform coffee table with the mug. Then Magic Desk application to extend the display area. A wall projection combining virtual post-it with the physical documents. A floor projection of images that is aware of user position in the museum exhibit. An augmented workspace that takes into account the presence of the physical objects, as well as an interface that adapts to a dishware. Despite of having positive results of system usability scale, the interaction is still limited, and only a few constraints are implemented. Also, other constraints can be added to address the other layout properties, such as balance or symmetry. Based on limitation, we're considering to add more constraints, such as user preferences, high-level semantics, or task requirements, as well as the constraints on multimodal interfaces. However, by adding more of them, will come the question of scalability of the optimization. Moreover, hierarchy of decals could be done in the future. Also, clustering a problem to a subset of decals allows for more efficient optimization. Thank you so much for your attention. And if you have any feedback or any questions, please ask.
Thank you so much for presenting this impressive work. I think most of us would like to have such a self-organizing desk and desktop. I think that sounds pretty amazing. I think we already have a few questions. I will just start with one from my side. So we know, for example, from design laws, right, that certain forms, shapes, and groups are perceived as belonging together, right? Did you already consider this, that when you now obviously place objects and you reposition them, that you might create a different meaning, one that might not be the intention of the user in the first place? Did you already consider this?
We will consider this one as the future work, because for now we focused just only on, let's say, primitives such as like icons, text, and images, and also we defined the shape of the content. But the semantics, as you are asking, And the perception will be done in the future work.
All right, thanks so much. Then I think we have a question from the remote participants. So the question is, the decals always look quite identical in their shape and size, even though being images or text. Did you think about what happens if you have to consider far more heterogeneous objects like documents with other aspect ratios and sizes?
Yeah, it won't be a problem to implement decals of any shape. We could use the, let's say, rectangular shape or like any freeform shape. So because we have the fill functions, we can implement any shape of the decals.
All right. Are there more questions from the audience? Yes.
Maybe I missed it in the talk, but I think you, the evaluation, you looked at different combinations of your constraints. And I think they were either present or not in the different conditions or that you, wouldn't it be also an option to change the weighting in the sense or the weight of each constraint and thereby create a much larger space for comparison?
Yeah, that's a nice observation. And this is also a kind of future work, is about more user constraints and like task requirements constraints, so which will be added up later.
Are there more questions? There's a question over there.
What happens if the user adds so much occlusion that some of the documents or decons can't be shown anymore? Is there like a sorting position which items are not shown first, or what does it depend on?
We were thinking about this one, and for this work, we just thought of kind of constant display area. But if we have too much of the decals on the display shape, so we can use the scale constraints. So let's say depending on the priority, or also like the priority is based on users, we can scale up or scale down some of the decals, or we can also hide them somehow, like minimize them. So it's also the kind of task constraint that requires just a specific amount of the decals.
Let's give a big round of applause to Aziz for his very nice work.